In this video, I'm going through S1, Chapter 4 and Section 4.8, and it's tree diagrams, and it's something that you should be very familiar with from GCSE. So a tree diagram can be used to show the outcomes of two or more events happening in succession, that is, one after the other. A bag contains 7 green beads and 5 blue beads. A bead is taken from the bag at random and not replaced. A second bead is then taken from the bag. So that type of question, the best thing to do is to do a tree. The first thing is always trying to find the total, which is the denominator. So it's 7 plus 5, which is 12. So the denominator is 12. So I've got green and I've got blue. And I've got green is 7 out of 12 and blue is 5 out of 12, and that's the first pick. And then out of each branch you should have another 2 branches, because you can again pick green or blue, and again you can pick green or blue. Now we consider the first branch and we say if the first pick is green, so we kind of don't look at what's below. If the first pick is green and it's not replaced, what has happened? Well, there are now 6, not 7 green, and there is a total of 11. Well, what has happened to the total? It is still 11, not 12, but the number of blue hasn't changed because I've only picked the green, so it's still 5. And you check 6 at 5 is 11. And then I do the same. I kind of go up and I block that top bit and I say, well, actually, forget that. If the first pick is blue, what has happened to my total if the blue is not replaced? Well, I start blue with blue, it's 11. And it's not 5 blue, it's now 4 blue. What has happened to the number of greens? The number of green hasn't changed. It's still 7, not 6, but 7, because all this top bit, we kind of consider it hasn't happened. This is an OR. And so I have 7 out of 11. And of course, going across the tree is an AND. So I want the probability of green and green. So both beads are green. That's the probability of green and green. So going across the tree, this is an AND. And of course, these two probabilities have to add up to 1. Each branch has to add up to 1. So the probability of green and green is 7/12 times 6/11. And that's 7 out of 22. If you do it on your calculator, it will simplify it for you. And then it says, find the probability that the beads are different colors. So what can you have? You can have the probability of green-blue, or, well, let's put green and blue, or the probability of blue and green. And of course, the word or, if you remember from GCSE, means I am adding them. So green, blue, 7/12 times 5/11, add blue, green, 5/12 times 7/11. It's the same thing. And again, if you put it in the calculator exactly how you see it, you will get 35 out of 66. And again, that type of question is very GCSE. Now, this says, let's make it a bit bigger. Maybe let's make the screen bigger. Okay. It says conditional probabilities can be represented on a tree. So the probability of A and is the first branch. The second branch is the probability of B. So this is now the probability, and of course when we go A, B, what we're doing, the intersection and, so and B, is the probability of A times the probability of B given A. Because B happens second, it is the probability of B given that A has already happened. So that's what this is talking about. So the probability of A and B is the probability of A times the probability of B given A. So the probabilities on the second branches represent conditional probabilities of B given that A has or has not happened. So let's have a look. The turnout of spectators at a Formula 1 race is dependent upon the weather. On a rainy day, the probability of a big turnout is 0.4, but if it doesn't rain, the probability of a big turnout increases to 0.9. The weather forecast gives a probability of 0.75 that it will rain on the day of the race. Draw a tree diagram to represent this information. So let's have rain and not rain, dry. And we're going to use B for a big turnout, and the complement of B for not a big turnout, a small turnout. So the first thing we have to do is put the whether it rains or doesn't rain, because that's the independent variable. The dependent variable is the turnout. So rain and not rain. We say that, well, we are told that the probability of the rain on the races is 0.75, which means not raining is 0.25 because they have to add up to 1. And let me put this over here. And then, there we go. Big turnout, not a big turnout. Big turnout, not a big turnout. So, on a rainy day, so this one, on a rainy day, the probability of a big turnout is 0.4. Which means that not a big turnout is 0.6 because they have to add up to 1. If it doesn't rain, so that's this one, not rain, the probability of a big turnout is 0.9, which means a small turnout is 0.1 because they have to add up to 1. So I've drawn my tree diagram, and I've noticed it's not like probability without replacement. I actually have to read the question and put the right probabilities on the right branch. Find the probability that there is a big turnout and it rains. So it rains and there's a big turnout. So the probability of big turnout and it rains is the probability 0.75 times 0.4, which is 0.3. It's the same thing. It's, you know, just because you have all of this doesn't mean that it's working any differently. It is the probability of R times the probability of big turnout given that it rains. So it rains and the probability that it's a big turnout given that it rains. But it's the same, exactly the same thing numerically. Don't even have to worry about that. Then find the probability that there is a big turnout. Well, the probability of a big turnout is this. Either it rains and there's a big turnout, which we've already worked out, by the way, it's that. Or it doesn't rain and there is a big turnout. So it's 0.3 plus this. So that is 0.25 times 0.9. And therefore, altogether, the probability of a big turnout is 0.525. And this one says, a bag contains 6 green beads and 4 yellow beads. A bead is taken from the bag at random. The color is recorded and it is not replaced. Okay, so it's not replaced. A second bead is then taken from the bag and its color recorded. Given that both beads are the same color, find the probability that they are both yellow. So given that, I've restricted the sample space, and the sample space now is a tree diagram. So let's put the tree diagram and just see what's going on. We've got green and yellow. 6 add 4 is 10, so it's out of 10. 6 green, 4 yellow. And then they're not being replaced, so green, yellow. So if I'm picking green first, it becomes 5 out of 9. The yellow stays the same, so it's 4 out of 9. If I am picking yellow first, it becomes 3 out of 9, and it remains 6 out of 9 for green. And I'm just gonna tell you how the book has labeled it. They've just said green 1, green 2, y1, this is y2, and this is green 2 and green 2, the second pick. So that's just a different way of writing it so that you are aware. So given that both beads are the same color, find the probability of yellow. So probability of yellow, given that they're the same color. Well, you remember the formula. Same color is our denominator. So we need to work out the probability that they are the same color. And then we need to work out the probability that they are both yellow and same color. So that's of course and. So the first thing I'm going to do is work out the same color, the probability of the same color. I like to work out the denominator first. So probability of same color, which is the denominator. So that's the probability of green and green, or the probability of yellow and yellow. So that is 6/10 times 5/9 plus 4/10 times 3/9. So this is 30 over 90 plus 12 over 90, which is 42 over 90. So that's what I'm going to divide by. I'm going to divide by 42 over 90. And then I want the probability that they're yellow and the same color. So basically I want the probability of yellow. The probability of yellow and the same color is the probability of yellow and yellow. That's what it means. So the probability of yellow and yellow is 4/10 times 3/9, which is 12 over 90. So the probability that I want is going to be here. 12 over 90 divided by what I found first, which is 42 over 90. And it's going to be 12 over 42, which is 2/7. And if you do it on your calculator, it will simply give you 2/7. So you're absolutely using the formula for something like that, but also essential to draw a tree diagram to see how everything connects to each other. And this is the final section, section 4.8.